All right, so the test statistic shows how far the sample results is from the null parameter value and in what direction on a standardized scale. You can use the test statistic to find the p-value of the test. In our free throw shooter example, the sample proportion is 0.64. It's pretty far below the hypothesized value, p equal to 0.8. So this is how you calculate the test statistic. You take the statistic, so you take the 0.64, and you subtract from it the null hypothesis, and then you divide by the standard deviation of the statistic. Remember that this standard deviation of the statistic is found, or calculated using values from the null. Okay, so they're going to be, remember this value right here came from the formula right here, p times 1 minus p over n, so it came from the square root of 0.8 times 0.2 over 50. That's how they got that value right here. Remember that the value we put in there was that actual population parameter from the null. So that's where that value is coming from. So technically, this whole statistic, if I had to do the calculation, would have looked like this: 0.64 minus 0.80 over the standard deviation of the statistic is the square root of 0.8 times 0.2 all over n, which was 50. Okay, so this value, this is where that number right there would have come from. Okay, so remember, you'd have to put in the value of the standard deviation of the statistic. You don't have to remember that. This right here is on your green sheet, so you're not having to memorize it, you just have to apply it. When you do that, you get the statistic of negative 2.83. This is a z-score. This is a standardized score, right? So this is a z-score. So I want to know what's the probability of getting this value or something more extreme. So what happens is that when I draw my curve here, and it's normal with the mean at 0.8, right, and the standard deviation of 0.0566, what's the probability of getting a negative 2.83 or something more extreme? If I want the area under the curve, which is a p-value, I'm going to have to use normal CDF here. Guys, I told you it's going to keep coming back. It doesn't go away. P-value is this area under the curve. You have to get this z-score thing first, and then you apply it using the mean and the standard deviation that you have of the assumed normal population. So the shaded area, and they go through that, and you get that this p-value then happens to be 0.0023. Right? So if H0 is true, a player makes 80% of his free throws in the long run. There's only about a 2 in 1,000 chance that the player makes as few as 32 out of 50 free throws. So it's almost impossible, right, for him to get that. It's less than a 1% chance that he would get the value he got or something more extreme, given that he really does make 80% at the line. That would say that there's enough evidence to say, okay, you can't really make 80% of the line, because if you did, there's almost a no chance that you would have only made 32 out of 50 shots. All right, so here's our 4-step process for significance test. Again, you're going to state the hypothesis test you want to do and the significance level. Notice the significance level has to be stated here. All right, you also define your parameters you want to use. So your H0 and your alternative get done in the state step. Plan, this again is where you're going to check your conditions. All right, if the conditions are met, perform your calculations. Get your your test statistic, and then find the p-value after you have your test statistic. And then we're going to conclude your results in the context of the problem. All right, when conditions are met, random, normal, and independent, the sampling distribution of p-hat is approximately normal with the mean of this and this. Okay, so this is how you find it. The null hypothesis specifies a value for p, which we will call p0. We assume that this value is correct when performing our calculations, so we always go with what the null says, and that's what I told you earlier.